Okay, so in today's class sessions, we're going to start our discussion of routing. We're going to look at some of the features first on the layer 2 switches and how they can route between VLANs and how they can use their native layer 3 routed interfaces. Then we'll get into static routing, start talking about the dynamic routing protocols. Then some of the other switching topics we'll come back to a little bit later once we get into some more of the services and application level type topics. So as we talked about before, the big difference between layer 2 switching and layer 3 routing is that the switches don't change the frames as they're moving between their interfaces. So if two ports are in the same VLAN and a frame is coming in one and going out the other, basically the only thing the switch is doing is looking at the destination MAC address and then choosing based on the CAM table or the MAC address table how it's going to send the frame. And this is the reason that we call this feature transparent bridging, because we're not changing anything in the headers. The issue with this is that based on the VLAN, or what's our broadcast domain, that's ultimately going to control what devices that we can reach. So when we look at the basic operation of an end host that's running IP, it's basically going to do a fairly simple decision process that it says, look at my local IP address and look at what the destination I'm trying to reach is. If the source of the packet has an address, let's say 10.0.0.1/24, and the destination is 10.0.0.2, then what the IP device internally does is it takes its own address, it takes its subnet mask, which in this case is 255.255.255.0, and it does a binary AND against these two. The result of this tells the host what subnet it's on. So this host now knows I'm on the subnet 10.0.0.0. It then takes the destination and does an AND with its own subnet mask. If these two results turn out to be equal, the IP host knows that the source and the destination are on the same segment, or they're on the same subnet. So this means that if this is the source A trying to reach the destination B, it's going to directly send an address resolution protocol request to try to figure out what is the IP address to MAC address resolution. If these results turn out to be different, it knows that it's not on the same subnet, and it needs to send the traffic where typically? To the default gateway. So it's going to send the address resolution protocol request to the gateway to figure out how do I leave my segment, and I'm going to use their layer 2 MAC address when I'm actually building the frames. So once it gets to the gateway, or what we consider either our layer 3 router or our layer 3 switch, this is where the changing of the packets happens, or what we call the layer 2 packet rewrite. So anytime the router receives a packet in and it needs to forward it out another routed interface, it's going to remove the layer 2 header that came in, and it's going to build a new layer 2 header depending on where it's going. So from an Ethernet switching point of view, this implies that traffic between different VLANs is going to have to be routed, and that the device is going to have to do this layer 2 packet rewrite. This would also allow us to have any type of design where the router has like a Ethernet LAN segment and then is going out to some other media like PPP or frame relay or ATM, where we know that these layer 2 protocol formats are not the same, they're not compatible. And this is one of the reasons why the router has to do that rewrite. That when the packet comes in, it's looking at the IP header, which is going to be made up of the IP source and the IP destination, along with some other fields. And on top of this, you have your layer 2 source MAC address. You have your layer 2 destination MAC address. But the router is going to be looking at this portion of the field, the IP destination. Then, depending on what that says, the router doesn't really care what the payload of the packet is. It looks at its routing table and determines what's the outgoing interface that I need to send the packet, or who's the next hop device that it needs to go to. So if the router says that the packet is moving this way, it needs to decapsulate, or basically remove, the layer 2 header that came in, and then rebuild this to a new layer 2 header with the source address as itself, and then the destination address of whatever the next hop value is on the segment. So we'll see, depending on what the particular media is, if we're doing Ethernet encapsulation versus frame relay or some of the other WAN encapsulations, the format of this is going to be different. Like PPP is a different formatting than Ethernet is, but the logic is always going to be the same, that we're removing the layer 2 header as it comes in, and then we're rebuilding it for it to leave on the destination segment. Now, in the case of the Ethernet LAN, there's a couple different solutions that we have for this. One of them is going to be to connect our layer 2 only switches to a dedicated router that's going to be doing the routing between the segments. And typically we're going to do this with just one physical link from the switch to the router, where we have the switch that's going to have multiple segments that go on to the access layer. So this would be our access level switch. And it has a port in VLAN 10. It has multiple ports in VLAN 10. It has some other ports in VLAN 20. If the switch is doing layer 2 only, it's not allowed to move frames between these interfaces because they're in different MAC address tables. So one solution to this is to send the traffic up to the router, have the router receive the traffic in one broadcast domain or one VLAN, rewrite the packet, have it come back down, and then go to the destination segment. Now this could be with one physical link, or it could be with multiple physical links. It depends on really the design of the physical topology. But the logic is going to be the same, that as the frame goes up to the router's job is to rewrite the packet at layer 2 and then to move it back onto the LAN segment. Now, as you could probably guess, the limitation of this is that for each VLAN that you're trying to route traffic between, you'd need a separate physical link on the router. And most of the time, it's not going to be feasible to dedicate one physical port on a per VLAN basis. So another solution to fix this is what we call router on a stick. Basically, we're trying to collapse the problem of having multiple physical links from the layer 2 network to the layer 3 network that we're trying to route between. So one of the ways that we can fix this is just by using one physical link and then breaking it into multiple logical layer 2 segments based on the VLAN number, which means that the layer 2 switch and the layer 3 router need to encode the VLAN number, which is the job of either the ISL trunking encapsulation or the .1Q trunking encapsulation. So the logic would be the same as before, where the switch looks at the layer 2 MAC address and sends it up to the router. When the router receives it, it's going to rewrite the layer 2 header, move it to whatever the destination segment is, and then switch it back to the layer 2 switch. So now instead of having multiple physical interfaces, we have these multiple sub-interfaces on the router, where as traffic is received in here, we're looking at still the IP destination, because the router is making its decision based on the layer 3 header. It looks at then what is the layer 2 MAC address of whatever the destination is. It leaves the IP header alone, but then changes the layer 2 header, or the Ethernet header, changes it to be whatever the destination that we're trying to reach. Question?
The router, somebody says, do you actually define a VLAN number?
You tell it what VLAN number uses is on the sub-interface.
Let's say it works service provider, they give you a VLAN, and they don't really know your IP scheme, but they don't know your VLAN number. Yeah, VLAN 10 and 20,
right.
But on the sub-interface, they do VLAN 1 and 2.
Then it's not going to work. So typically the routing would be on your side. So this is like the LAN that you're in charge of. Then this would go out to whatever the service provider router is. But between these two, you're running just layer 3 routing. So they don't need to know the details of your layer 2 network. There are some other solutions for this that try to simplify the design for the customer, where you could have a layer 2 switch on one side that has VLAN 10 and VLAN 20, and then a layer 2 switch on the other side that you're trying to span these VLANs between them. And if you connect to the service provider over this network, they could basically offer you a layer 2 tunnel over their network, where from your perspective it looks like at Ethernet your switches are directly connected, but you go over multiple hops in their network.
That's actually not my question. My question was on the router, right?
On the router, right.
Your interface and fast Ethernet interfaces, right?
Right.
I'm talking about on the fast Ethernet interface, the subinterface, .10,
Right.
.20, right? They have .1.
The number here, the actual subinterface number is arbitrary.
I'm sorry, they have a VLAN 1
Right.
on the left and VLAN 2 on the right.
Right.
For us, we have VLAN 10 and VLAN 20. But I do have the IP address are on the same. I say, for example, on the router .10, right, you have 10.1, 10.0.0.10.
Right.
And on the VLAN side, we have
You have an address here on the switch.
Right.
That's an IP address. Then this segment is routed. So it's not, the switch is doing the rewriting of frames, not the router on this side.
I see.
So if it's a layer 3 link between them,
It doesn't matter.
then it doesn't matter what the VLAN number is because it's not, you're not spanning the spanning tree, or you're not trying to span the VLAN.
Got it, okay.
So this would be used just for native layer 3 routing. But in this type of design with router and a stick, the end host here basically would be pointing their gateway at whatever the router's address is assigned on the subinterface. So the traffic stays on the local segment and it's layer 2 switched up to this subinterface, and then the router is going to move it between these segments. So the configuration for this is fairly straightforward. The considerations that we need to take into the design are that this interface on the switch, we need to make sure that this is running trunking. And that whichever protocol we're using, if we're using .1Q or if we're using ISL, we just need to make sure that the router and the segment and the switch agree on this, because it's a different layer 2 protocol format for ISL versus .1Q. The other thing that we would want to do is typically limit the layer 2 VLAN numbers that the switch is trunking to the router, because otherwise if we have VLANs 30, 40, 50, etc. and the rest of the network, the router is going to be receiving on the physical interface a bunch of traffic that it's not actually going to use. And as we talked about before, that's one of the jobs of VTP pruning, which is to limit the layer 2 traffic over your trunk links. The problem is the router doesn't run VTP pruning on its routed interfaces. So on the switch in this type of design, we would typically want to use the switch port trunk allowed list command and then limit it to only the particular numbers that the router is actually encapsulating. Because otherwise it's going to get broadcast frames and unknown layer 2 frames that it receives on the interface and just throws away because it's not using that particular VLAN number. So let's take a look at it in an example of this here, where we have router 1 is going to be doing the routing for the segment. And physically this is connected to switch 1. On switch 1, this is fast Ethernet 0/1. On router 1, this is going to be fast Ethernet 0/0. And let's say that we're trying to get traffic between router 3 and router 5. So they're all sharing the same physical layer 2 switch. This port here is fast Ethernet 3. This port here is fast Ethernet 5. We'll say this side is VLAN 10. This side is VLAN 20. So from basically what is the end host point of view, in this case router 3 and router 5 would be the end hosts. What I'm simply going to do is that if we look at their current configuration, let's say show IP interface brief, we'll use this as our VLAN 10 address. We have 10.0.0.3. And normally on the regular routing iOS platforms, the routing feature is on with IP routing. If I were to turn routing off, now it's going to act as if it was just an end host in the IP network, where we could set the IP default gateway, and I'll set this to router 1's address. So essentially now when router 3 makes its routing decision, it doesn't look at any type of protocols like static routing or dynamic routing. It just says, look at my gateway, look at my address that I have assigned, do the binary AND between my address and my subnet mask, do the AND between the destination and my subnet mask. If they end up to be on the same segment, then I can just use layer 2 directly to reach them. But if they end up being on different subnets, I'm simply going to send my traffic to the default gateway. And then it's their job to route the traffic between the different links. Router 5 is basically going to do the same thing here, where if we look at its current configuration, basically doesn't have anything. So I'm going to turn routing off, no IP routing. At the interface level, the address will be 20.0.0.5 for router 5. And the IP default gateway will be router 1. We'll say 20.0.0.1. So the key here is that we have two different subnets. For the VLAN 10 side on router 1, this is going to be 10.0.0.1. On router 3, this is going to be 10.0.0.3. Then on the VLAN 20 side, router 1 has another address, 20.0.0.1. Router 5 has 20.0.0.5. From the layer 2 switches point of view on switch 1, I would then need to make sure that my VLAN assignments are correct, because otherwise I'm not going to be able to have the devices be in the correct broadcast domains. So I need to know that I have VLAN 10 and I have VLAN 20. Then at the ports that go down to the end hosts, these would be access ports that are in that particular VLAN. So switch port mode access and the switch port access VLAN assignment. Same thing on router 5's port, except we're in a different VLAN number. If we were to go to the end host, like on router 3, and look at the debug ARP, we should see that we would not be able to reach router 5 because the router is not going to send the ARP for someone that's not on its local segment. We'll see when we get into some more details of the routing techniques a little bit later. There are some kind of tricks that the router tries to do to automatically fix this. But in most cases, the router shouldn't be sending ARPs for the final destination for 20.0.0.5. Instead, what we see it doing is trying to ARP for who? Router 3 says, look at what the destination of the packet is. It's 20.0.0.5. This is not in my subnet. My subnet is 10.0.0.0. My gateway is 10.0.0.1. So it tries to do the ARP for router 1 to figure out what's one's MAC address. It's the device that's supposed to do the routing for us. Now, right now, the entry ends up being incomplete if we were to show ARP because I don't have router 1 configured yet. It doesn't have this address in that particular VLAN. But likewise, router 5 would be doing the same thing. If we said debug ARP and were to ping 10.0.0.3, we would see that the ARP request should go for the gateway, which in this case is 20.0.0.1. So this is what your end host is doing, like your Windows PC or your IP phone or whatever is the end application that's running the IP stack. So now between router 1 and the switch, this link needs to carry those multiple VLANs. So I'll reset the configuration from what I had there. So the interface is the default. At the link level, I would need to make sure that this link is running in trunking mode, where by default these interfaces are going to be in dynamic mode, which means the switch tries to negotiate, is it an access port or is it a trunk port? But the problem is, in this type of design, the router here is not running the dynamic trunking protocol, so it can't detect that the switch is trying to automatically do this. So we need to tell the switch basically just to statically nail this up as a trunk link. And to do that, we need to tell it what the encapsulation is, because we can't automatically negotiate the encapsulation if we're not running the dynamic trunking. So we would say switch port mode trunk and the switch port trunk encapsulation. So whichever variation we want to use, .1Q or ISL, the end result is going to be the same, that the VLAN number is encoded. More commonly, you would use .1Q simply because you're pretty much guaranteed that all platforms are going to support this. Not all platforms, even not all Cisco platforms anymore support ISL. They're starting to phase this out. So from the switch's perspective, just a couple commands there. The link is trunking and it's using .1Q encapsulation. From the router's point of view, we're now going to need to have two separate sub-interfaces, where the main interface, if we show run interface fast Ethernet 0/0, this would not get an IP address because we need to assign the separate logical sub-interfaces where the VLANs are going to be encapsulated and then tell the router what is the addresses that are for those separate segments. So we would have separate sub-interfaces. The numbers themselves don't matter. It's an arbitrary number. Most of the time you would see that this matches the VLAN number just for the clarity of the configuration. So if I see subinterface fast Ethernet 0/0.10, it would make logical sense that that's for VLAN 10 instead of saying it's .12345. So from here we need to tell the router then what VLAN number do you want to listen for. That is the encapsulation, what's the protocol, are we running .1Q or ISL, and then what's the VLAN number. In this case we're using VLAN 10. We then have an IP address, 10.0.0.1/24. We have the same thing for the other subinterface, where that's going to be for VLAN 20. This is in a separate subnet, which is the 20 subnet. Now, assuming that on the layer 2 switch, there's no problems with the actual VLANs or there's no problems with spanning tree, when we look at the show spanning tree for VLAN 10 and the show spanning tree for VLAN 20, I need to make sure that both of these numbers are forwarding on that link that's connecting to router 1. Where normally these would be designated ports, because router 1 is not running spanning tree, it's now a downstream facing interface, but I need to make sure that both of the numbers are actually being sent. So VLAN 10 is being sent, that's part of our multiple spanning tree config. Likewise, VLAN 20 is being sent, part of that same MST instance. If we were to show spanning tree interface fast Ethernet 0/1, it tells us here what are the different VLANs, or in this case, what are the different instances of spanning tree that we're running. To make this a little bit clearer, what I'm going to do is roll back to our previous version of spanning tree, which is the spanning tree mode per VLAN spanning tree. This would be the default on the switches. So now on switch 1, if I were to look at the show spanning tree interface fast Ethernet 0/1, it shows me that there's all these different VLAN numbers that are being sent to router 1. The issue with the actual efficiency of the network in this design is that these two numbers are being used on router 1's side, but these other VLAN numbers aren't being used. So any broadcast or any unknown frames that go inside of VLAN 30, 40, 50, or 60, router 1 is still going to have to get these. Then the Ethernet interface driver is going to figure out, well, it's a broadcast, so I have to listen to it. But then when we look inside the payload, it realizes it's not destined for itself, so it throws the frame away. But the problem is it still takes some processing for router 1 to figure out that the frame is not for me. It's really for somebody else. So typically when you're trunking from the layer 3 device to the layer 2 device, you don't want to have these extra numbers that you're not using. Question?
But don't routers discard all the bad channel traffic, whether it's VLAN 10, 20, or...
They don't route it between interfaces. They don't necessarily discard it because they need to figure out, is it for one of the applications that I'm using? So let's say, for example, that the router's running RIP version 1. It would be listening for broadcasts that would be going to the UDP port for RIP, which is UDP port 520. Or if we were running, like you said, like the IP helper address, and we were listening for our boot P traffic that goes to UDP 67 and UDP 68. This is for the DHCP traffic. So the router would be listening for that. The problem is that you have to take the layer 2 frame and pass it up to the higher layers to see if they actually want it. Where the router passes it up and says, I'm not running whatever that application is, and then it throws it away. But the issue is that it still ends up processing these, and it makes it inefficient bandwidth usage on the link, and then also inefficient processing on the router. So typically in this design, how could we fix this then? We would change the trunking allowed list so only these two numbers are included. So we would say the switch port trunk allowed list is VLANs 10 and 20. The only disadvantage of this then is that if you change the configuration later and add more subinterfaces on the router, you just need to make sure to update this. Otherwise, it's not going to be able to receive that traffic. So again, it's that difference in the ease of the management versus the efficiency or like the security of the network. This is going to be the better design, but it's going to take more maintenance in order to keep track of it. So next, let's go to router 3, who we were looking at the debug ARP. And we should now be able to reach router 1. We see that router 3 is saying, I'm trying to reach this address. This is my layer 3 address. This is my layer 2 MAC address. I'm trying to figure out what is the MAC address of router 1. Router 1 receives this frame because it's going to that all Fs at layer 2. Router 1 says, this is my IP address, this is my MAC address. It's going back directly to router 3, so it's a unicast reply. This should now mean that router 3 knows the MAC address of 1, and that 1 knows the MAC address of 3. If we show ARP, we can see it knows to get to router 3, it's located on this subinterface, and this is the MAC address. It's that all zeros in the 3 that I changed it to. The same would be true on router 5. If router 5 tries to reach 20.0.0.1, we should send the ARP request. Router 1 replies saying, this is my address. Now 5 and 1 should know each other. Where I know this is 5's address, I know this is 3's address. If we look at the MAC addresses that are used on router 1, we would actually see that the value is the same between 5 and 3, where it says 10.0.0.1 goes to this 0011 address. When router 5 looks at the CAM table, or not the CAM table, the MAC address table, these two values are the same, which is okay though because they're in 2 different broadcast domains. So the router is using the same MAC address for its multiple subinterfaces, but it doesn't matter because those MAC addresses are link local to that segment. The only people that care about the MAC address for VLAN 10 are the devices in VLAN 10. When it routes between the segment, it's going to change to an address that's significant now to that new link. And again, you could change these if you wanted to. There's usually not a reason that you need to, but I could say the MAC address here is whatever, all zeros and the 1. Then if I clear the ARP cache, this should send a new unsolicited reply to 3 and 5, and this is going to update their cache, where now if I show ARP, router 1's address resolves to the all zeros and the 1. Same thing on router 5. So we can see it's using the same address. On the router subinterface, it actually didn't give me the option to change the MAC address because it knows it only needs 1. Separate subinterfaces are always going to be separate broadcast domains, so there's no reason to have different addresses for the different segments. So next, let's look at the routing. At this point, router 3 again is going to say, for anyone who's inside my segment, I'm going to send the traffic directly to them. For anyone who is outside of my segment, I'm going to send the traffic to router 1. It's up to router 1 to route the packets between the links. So we're assuming that at this point, router 1 has the routing process on. And if we show IP route, it knows that if a packet comes in going to 20.0.0.5, that I should move this to fast Ethernet 0/0.20 and then rebuild the layer 2 header for whatever the MAC address of this destination is. So on router 3, if I were to now ping 20.0.0.5, now router 1 is routing the traffic on their behalf. We could actually see the packet level information on router 1 if we were to go to the interfaces and turn Ceph off. If I were to say no IP route cache, this forces the router to go back to the fast switching process, which would then allow me to look at the debug IP packet. Because normally on the router, when you look at a debug, it only shows you the traffic that is going to the router or coming from the router. That's always going to be the process switch traffic. Normally, traffic that is moving between interfaces, it comes in one link and goes on another one. You wouldn't see this in a debug output because it doesn't hit the general purpose CPU. It checks the Ceph process to figure out how you switch the traffic between the interfaces. So in a production network, you wouldn't want to do this unless you have like a network down emergency to begin with, and you have no other tools to try to troubleshoot what's going on. Otherwise, if you do this, you're just going to make the router's CPU shoot through the roof, and it's going to start dropping packets. But from our point of view, since we don't really have any application flows, we can look at some of the details of this. So if I were now to ping 20.0.0.5, router 1 should see these packets being received, and this shows us that it's routing it between the two interfaces. Where the IP packet came in from the source address 10.0.0.3, it came in fast Ethernet 0/0.10. The destination of the packet was 20.0.0.5. My routing process, which is the routing table, or what we sometimes call the forwarding information base, or the FIB, the forwarding information base told me that the destination is reachable out fast Ethernet 0/0.20. The next hop value, or the gateway from the router's point of view, is that host directly, because it's saying that the destination is actually attached to my segment. If there was another router between them, if I had router 3 going to router 1 to router 2 and then to 5, the IP packet would still stay the same, where it's coming from 3 and going to 5, but router 1 would say to get towards the final destination, I need to go to whatever this address is. And that's what it would show in this, this gateway field. If we were to look at the debug IP packet detail, this shows you the additional layer 3 and layer 4 information about the packet, where if I were to do a ping, it should tell me what is the IP protocol number, where the protocol number here is going to be for ICMP. It also tells me what is the ICMP type and the subcode, where this one here is the echo, or basically the ping. This one here, type 0, code 0, this is the echo reply, or the ping reply. So we'll see as we look at some of the details of the other protocols that we're going to be running. This is how you can see some of the low-level information behind them. So what is the layer 3 transport that they're using? What is the layer 4 transport? Like, is it UDP or TCP? And then what are the individual port numbers? It can be useful in certain circumstances to track down some problems with the application flows.
Hey Brian, when the originating device doesn't know the MAC address of something, it does a broadcast and find, or an ARP to find it, which shows up as a broadcast.
Right.
But when it knows it's off the subnet, can it just do a unicast to the gateway, or is it still a broadcast?
The layer 2 is a unicast to the gateway. The layer 3 would be a unicast to the final destination. So when we look at this design where we have, from a logical layer 3 point of view, we have router 3 basically as the end host. And then it's attaching to router 1. And then the end host on the other side is router 5. At this point, when we're looking at layer 3, the details of the layer 2 network don't matter anymore. As long as the frames can get from 3 to 1, we don't really care how they get there. So when 3 is sending this ping, it says that the IP source address is 10.0.0.3. The IP destination is 20.0.0.5. So it's going directly between 3 and 5. Then the MAC address source, whatever router 3's MAC address is, I had it configured as 0000, 0000, 0003. The MAC address destination is who? Is the gateway's address. So in this case, it is router 1. This here is a layer 2 unicast. So it's going from the sender to the next hop on the network. This here is the layer 3 unicast. So the router is not changing this field, it's just going to be changing this field. So when 1 gets the packet, it's going to say, I need to change the source to be my address. So now the source becomes whatever 1's MAC address is. And then the destination becomes whatever router 5's MAC address is. And this is mainly the job of the router, to do that layer 2 translation or the layer 2 packet rewrite. Now, as you can guess, the limitation of doing this in today's networks is that you need not only your dedicated layer 2 switches, but then you would need separate layer 3 routers in order to do the job of this. So in most networks today, these two devices are going to be collapsed into one, which is going to be a layer 3 switch. And the layer 3 switch is going to use the switch virtual interfaces, or the SVIs, basically to route the traffic between its local VLANs. This is what we configure as the layer 3 VLAN interfaces. So in some of the higher level platforms, this is what like your route switch feature card or your multi-layer switching feature card is designed to do. In the case of some of the lower level platforms, like we have the 3550s and the 3560s, these are basically our access layer, layer 3 switches. They're going to be using these switch virtual interfaces, or basically interface VLANs, to assign layer 3 addresses and then to do the rewriting between the segments. So now we're just taking these, what used to be two physical devices, and now we're collapsing them into one logical device, where the result is going to be the same, that if I were to go to router 1, and I'm going to remove its configuration. So router 1 is no longer routing for these two segments. The subinterfaces are deleted. This means that the end hosts won't be able to reach each other anymore, because there's no router to move the frames between the segments. But the switch can do the same thing. As long as the IP routing process is on, which on the switches it is not on by default. If you show IP route and you see the output says something about the ICMP redirect cache, this means the routing feature is off. So this would be the first step. You need to turn routing on. Now when I look at show IP route, it's going to show you the regular routing table output. It means that the IP process is now routing. So now from the switch, I would configure the interface VLANs, interface VLAN 10, with that same address that the host is using as its gateway, and interface VLAN 20. From the host point of view, it's going to be transparent. When router 3 now goes to send the traffic to 5, they don't really care that there's a different layer 2 device in the middle. As long as they update their ARP cache to whatever the new MAC address is, the end result is going to be the same. That now the layer 3 switch is receiving traffic in the access port. It says this access port is part of VLAN 10. So look at the destination MAC address. If the destination MAC address is my SVI, I know that the packet needs to be routed between the segments. So now in this case, the switch would have a MAC address in the CAM table for that VLAN, because it's doing two separate functions. It's doing the layer 2 switching plus the layer 3 routing.
It's a different MAC address for each, it's a generated MAC address, right?
I want to say that the switches do use separate ones,
For each VLAN?
which it does for each VLAN. So if we show interface include VLAN or BIA, you see that it does have for VLAN 1, it's using 9A40. For VLAN 10, it's using 9A41. So it has some sort of pool assigned internally. Then depending on which interfaces you're actually using, it's just going to automatically allocate an address to it. You technically don't need to do this, though. You could change the MAC addresses to all be the same. It's just that for this particular platform, it uses different ones automatically. From a layer 3 troubleshooting point of view, it makes it a little bit easier to do it this way. So if you don't have the same MAC address used over and over and over, you have like a one-to-one association between them. And if there's a problem with the address 9A41, I know that it's specifically this VLAN interface.
And you can modify those, like if you wanted to associate them closer, like you can make it 9A10 or 9A20.
I should be able to. Let's say for interface VLAN 10, MAC address, this platform doesn't allow you to do it. So it depends on the individual hardware. Some of them will allow you to do it, not all of them. can. But really, from the in-host point of view, they're not going to care because ARP is going to take care of this automatically for you. As long as they can do the layer 3 to layer 2 mapping between the gateway and the MAC address, they don't really care what the MAC address is. From our point of view, usually the IP address is going to be more significant because this is what we use for the routing, and then any of the other resolution features, like maybe our DNS entries or information we need to put in the DHCP scopes. This is the stuff that we care about. We don't usually as much care about the layer 2 addresses. Now the switch also does support what we consider a native layer 3 routed interface, where we looked at this yesterday when we were doing the Ether channel configurations. And a native routed interface is when you simply go to the link level and say turn the layer 2 switching feature off or make it not a switch port. In this case, once the physical link, like interface gig 0/1, has the no switch port command, we could then configure an IP address directly on the link and then use this in the layer 3 routing table in order to move packets between the interfaces. Again, as I talked about earlier, one of the, and actually it's listed on this slide towards the bottom. This document here talks about some of these design issues. That when you're using a native routed access layer, and then you extend your layer 3 routing protocols like eRGRP or OSPF down to the access layer switches, the idea behind this is that when we look at our 3-layer hierarchy of going from the core to the distribution and then down to the access layer, what we can do is that at the access layer, configure the interface VLANs, so interface VLAN 2, 3, 4, etc., for whatever the access ports that the hosts have assigned. Then the hosts are going to use the access layer switch as their default gateway. Then the uplinks that go to distribution, these are native layer 3 interfaces, where I would have an IP address, let's say 100.0.0.0/24 here, and 100.0.1.0/24 here. What this allows you to do is to take spanning tree protocol out of the picture. That from the access layer to the distribution, you no longer have to use layer 2 spanning tree for your convergence. You then use your layer 3 routing protocol. So if there's a problem and one of the links goes down, it's up to eRGRP or it's up to OSPF in order to do that convergence. Or if the entire switch goes down, the routing protocol is going to figure that out. And the advantage typically of doing this is that at layer 3, you're already routing IP. So in your network, you're probably running a dynamic protocol already. You're probably running eRGRP or OSPF most of the time. By having additional layer 2 convergence with spanning tree, you're just adding extra complexity to the network that doesn't really need to be there. And since these access layer switches can typically do layer 3 routing just as fast as they can do layer 2 switching, then it doesn't make sense to have to keep 2 separate protocols in the mix with the layer 2 spanning tree design and the layer 3 routing design. The only limitation with this, though, is going to be if you have those applications that need direct layer 2 attachment between their services. Like if you have some sort of like switch that goes to your servers, and attached here you have like your VMware machines, and then somewhere else in the network, if they're trying to talk to storage, most of the time this has to be a direct layer 2 attachment between them. There's some hacks and workarounds for this that you could use routing to fix it, but from the server point of view, they don't really take this into account a lot of the times. They just figure you're going to be able to reach between the server and the storage like natively over layer 2. So if you introduce layer 3 routing between them, then it adds some more complexity in the design. But as just an enterprise network, if you're servicing just like your end hosts and your IP phones, then you can do the layer 3 routing design like this, and then just use your routing protocol in order to deal with any of the convergence problems. And again, that's what this document talks about, the high availability campus network design using the routed access layer talks about. So the advantage of doing this is that when you turn the port into layer 3 mode, it's going to be treated just like an Ethernet interface on the router. So you can put IP addresses on there, you could do layer 3 access lists, you could do layer 3 quality of service. Most of the features that the router supports is going to be identical to what the switches are going to support on their interfaces. So if we were to take the design that we currently have and try to extend this, let's say now that the VLAN 20 is going to be on a different switch where we have, or let's not even say VLAN 20, let's say a different one, where right now we have switch 1 that is connecting to router 3 and router 5, where these are in VLANs 10 and 20. Then we'll have another physical connection that goes to a different switch, let's say switch 2, and then this connects down to router 4. We'll say router 4 is going to be in VLAN 30. So we'll use the address 30.0.0.4 here, /24. The switch then would typically have a VLAN 30 interface that would be the default gateway of those hosts on the access segment. But then here on the uplinks, we're going to run this as native layer 3. So there's no layer 2 spanning tree convergence. There's no MAC address table sharing between the switches. They're basically independent layer 2 devices in the network now. So on switch 2, I'm going to configure VLAN 30. This is going to go down to router 4, so switch port access VLAN 30. Then a VLAN 30 interface, say 30.0.0.1. This would be what the end hosts are going to point their gateway at. So just like the other routers, router 4 would say no IP routing, because they're acting like end hosts now. And on the LAN interface, the address is 30.0.0.4. And I should now be able to reach just that address that's inside my same VLAN. So once the switch converges layer 2 spanning tree, now there's reachability on this segment here, directly between them. Now I should not be able to reach router 3 in its subnet, and I shouldn't be able to reach router 5 because there's no routing set up yet between those two networks. So now instead of expanding the layer 2 domain between the switches, we need to break it up into different layer 3 networks, where between switch 1 and switch 2, one of the sets of interfaces here is Fast Ethernet 0/13. We'll use that for our routing. If we look at the current configuration, that's part of a channel group. Let me get rid of this. We'll say no interface port channel 1 and default interface Fast Ethernet 13. So that's resetting it to the default. Same thing on the other switch. Default interface Fast Ethernet 13. So now on these two interfaces, I can treat them just like normal router ports, where I would say no switch port, which means that the switch port access VLAN command or the switch port mode trunk, or basically any option that's under switch port, this no longer applies to the interface because it's not running layer 2 switching. It's doing just layer 3 routing. So we say no switch port, and then we can put an address between them. Let's say any address, 100.0.0.2 for switch 2. And on the other side, in the same subnet. So no switch port, IP address 100.0.0.1. When we now look at the routing table, not only do we see our virtual VLAN interfaces, or the switched virtual interfaces, we also have the native layer 3 routed port. So it's treated just like any other interface in the routing table. This means that if I were to send traffic to someone on that connected segment, like the other side, which I configured as 100.0.0.2, we should see that switch 1 and switch 2 have reachability to each other because they're now in the same layer 2 and layer 3 network on that segment. So switch 1 is saying, this is my MAC address, this is switch 2's MAC address. This is my IP address, this is their address. So now as a packet would be received in from router 3, if it's trying to get to router 4, what switch 1 would be doing is rewriting the destination MAC address to this value, to whatever is the next hop layer 3 device in the network. But then at this point, we need to run some sort of routing protocol. Whether we're doing static routing or whether we're doing dynamic routing, we need some way for switch 1 to realize that the network 30.0.0.0/24 is reachable via this next hop. And likewise on the way back, that switch 2 needs to know that the VLAN 10 segment and the VLAN 20 segment are reachable via this hop. Where this could be solved as simple as doing static routing, like I could say to get to 30.0.0.0/24, use 100.0.0.2, and then on the way back, have multiple routes that say to get to 10.0.0.0/24, use 100.0.0.1. So this is switch 2 saying use this interface to reach this subnet, and this interface to reach this subnet as well.
Is IP routing enabled by default?
On the switches, it's not. So you would need to say, I said separately before IP routing on its own. You can tell if routing is on when you look at the show IP route. If it shows you this output here, it means that routing is on. Now I have two static routes. It says to get to the 20 network or the 10 network, I'm using this next hop value, which basically means use the layer 2 MAC address of this device in order to reach any of the layer 3 packets that are going here. So now the switches are rewriting the layer 2 frames with each other's MAC addresses as they go between segments. And router 1 now should be able to reach the 30.0.0.4, which is, or not router 1, router 3, 30.0.0.4. If the routing is working properly. So let's say now there's, as we can see, there's a problem in layer 3 reachability. If I want to try to track down exactly where the problem in the network is, the best way to do this is to use the process of elimination and try to look at first, from router 3, can I reach that interface? If I can reach this connected interface, I know it's not a layer 2 problem between me and the gateway. Then I want to know, can I reach their interface that they're using to get to the next hop? This would tell me that there's nothing wrong with the assignment of the address here, and there's nothing wrong with the routes back to me. Then I would check the further next hop. If I can reach this, it's telling me that the layer 3 routing is working between these devices and that switch 2 has a route back to me. Then I could check, can I reach this one, which means I know the route to this segment, and so on and so forth. So it makes it a little bit easier to track down exactly where what device is the problem related to. So I want to know, can I get to my gateway, which I can. Can I get to the link that they are using to reach the other switch, which I can. If I can get to switch 2, it means it's not a routing problem back to me. If I can reach their VLAN interface, 30.0.0.1, it means I now have reachability all the way up through to this segment. But if I can't reach 4, then it's probably a problem on 4. So let's check the routing config on 4.
Routing config?
Well, the layer 3 configuration. So if we show IP route, routing is off, but I didn't set the default gateway. So let's say the IP default gateway is 30.0.0.1. This basically would be an indication like your end host has a problem. So now router 3 should be able to reach them. Where, let's see if this is even the correct address. Can I ping 30.0.0.1? I can reach them. Let's see, can I reach 100.0.0.2? So router 4 can get here. Can I get to 100.0.0.1? Which I can. I then should be able to reach 10.0.0.1. That's the VLAN interface.
Just routing the switch.
This most likely means that there's a routing problem on the other side. So let's look at, maybe I put the static routing statements in incorrectly. If we look on switch 1, let's say show IP route. I have a static route for the 30 network to get to 100.0.0.2, which 100.0.0.2, that should be my connected neighbor. If I were to do the trace route from this side, that would show me any of the problems with the hops along the way. I should at least be sending the traffic to my directly connected gateway. Probably what this means, I would bet that router 4 actually has this address assigned on a different interface from before, which it does. So it was sending the packets out the wrong interface. What I should have seen here, at least that I got to the first hop, but since it didn't show up as 30.0.0.1, that's an indication that it's not even going out that link to begin with. On router 4, if I were to look at the debug IP packets or debug IP packet detail, when I ping 10.0.0.0.1, the routing process should tell me that it's trying to go out fast Ethernet 0/1, but the encapsulation is failing. This means that there's a problem in your layer 3 to your layer 2 resolution, where router 4 thinks that the destination is in the same subnet as it, so it's trying to do what? It's trying to do ARP. But the ARP process is returning an error saying, I don't know the MAC address of 10.0.0.1, so the routing process says, I can't build the layer 2 frame. And this is what an encapsulation failed means. So the problem here is just that router 4 shouldn't have that address on the interface. Now if I ping 10.0.0.3, now the routing works. So if we were to look at this output of debug IP packet on a hop-by-hop basis, the layer 3 information is not going to change. So the packets are always coming from here, going to here, and then they're always returning. What the devices in the middle are going to be doing is changing the MAC addresses, not changing the layer 3 header. There are some minor things in there that they'll change, like the IP time to live. That's going to be decremented on a hop-by-hop basis. But the source address and the destination address, this is not going to change. Only the layer 2 source and destination would change. So now if router 4 were to do that trace route, to trace to 10.0.0.3, we should see how many layer 3 hops are in the network, where it's saying I first have to go to 30.0.0.1, which is my first hop. Then I'm going to 100.0.0.1, which is my second hop. Then I'm going to the final destination, that's the third hop. So, go ahead.
Can
Go
you
ahead.
source the trace route from an interface?
You can change it if you want to. If you say trace, and then you can either do, you can do two things. You can say trace route and then just press enter. This will ask you all of the options. Or you could say trace 10.0.0.3 Then a question mark, it'll give you some different options, like what's the source, what's the port number you would use, how many times you tried to ping them, what's the TTL of the packet. The same would be true of ping, that you could change some of these options. Most of the basic tools on the router you can do this for, like if you were to do this for a telnet, you could also say, what's the source interface? One thing we'll see that's really useful about telnet is that you can change the destination port number, so you can use it for testing different TCP applications. One of the things we'll see is that when we look at BGP routing, you could telnet to a destination at port 179, and that'll tell you if it's running the BGP routing service in order to form a neighbor relationship. Like if you wanted to test, do I have reachability to my web server, you would telnet there at port 80. And this actually means that router 3 is running the web service. You can see we get an HTTP error message as a return code. Okay, any questions up to this point on the routing with the sub-interfaces, the router on a stick, the VLAN interfaces, or the native layer 3 interfaces? Where when we look at the final configuration here, there's not that many changes that we need to make. This is the switch virtual interfaces, and then this is the native layer 3 interface. We just need to say no switch port. Beyond this, it's going to be normal routing configuration, like static routing, dynamic routing, any of the other features that go along with that.